Very good, Monica. If you have any WhatsApp group, ask your friends to join. We'll wait for 1 or 2 minutes and we'll start the session. Okay. What are the topics that we have seen in the previous class, Ma? In contact session 1, what are the topics that we have discussed? Do you remember the topics? What is the architecture? What's a network? What is a network architecture? What are the functionalities? Right. The network functionalities, the components, network structure, what will be there at the edge of the network, what will be there at the core of the network. Okay, the protocols used, what are the interfaces? We have seen what is encapsulation, the graph, protocol graph, OSI architecture. Okay, the difference between guided media and guided media. What is internet? Internet structure, internet architecture, the ISPs, internet service providers, and what are the goals for the internet architecture, design goals of the internet, and what has to be given for the future. That's all the things that we have seen, the next generation internet design, the requirements. Those things we have seen in the previous class, right? So we'll start with today's class. Whether my screen is visible, Ma?
Yes, ma'am.
In today's class, we're going to recap the TCP, transmission control protocol. Okay. So why will the transport layer will be having three different protocols? What are the protocols supported in transport layer? What are the protocols supported in transport layer, Ma? Ma, the protocols supported in transport layer are students, are you there in the meeting? Just now we have discussed what is the recap that we are going to see. What is the protocols supported in transport layer? TCP, UDP, and you have one more protocol, Roy. That is ac2 as well. Yes, you would have studied these two things. Um, it is not a familiar, ac2 is not a familiar one, but transport layer supports three different protocols. So it supports TCP, UDP, and ac2. Okay, transmission control protocol, user datagram protocol, and stream control stream control transmission protocol. Okay, so these two things are connection oriented protocols, and this is a connectionless protocol. Okay, so transport layer, transmission control protocol, and stream transmission protocol, both are connection oriented. Okay, so why we need to give two different approaches? Why we want to concentrate in connection oriented and also connectionless? So why it is required? So why do we need two different protocols? One works for connection oriented services, one providing connection oriented services, another providing connectionless services. Why? Because the applications they have different diverse needs. Okay, some needs the correct connection oriented, they need a guaranteed service. Okay, so for example, I'm transferring a file. Okay, file transfer is happening. So it should be a guaranteed one. Okay, if the file that has been shared, if it is not at not reached at the destination, there is no need of sending the file, and also it needs accuracy. Okay, so other voice video conference, they need speed as a priority. Okay, so it also needs a minimal delay. Okay, that's why we use two different protocols. So transmission control protocol and user datagram protocol to support different types of data transmissions. Okay, so say for example, remote login, email, file transfer, they need a reliability service. Okay, so if I'm gonna use SSH for remote logging, simple mail transfer protocol for email, or file transfer by using FTP. So all needs accuracy and also data integrity. So any missing or any uncorrupted data, it will cause failure or security issues. So that's the reason this sort of applications, they require transmission control protocol. So all the data packets that have been delivered uh, has to be, it should be acknowledged by the receiver that the receiver has received the packets, and also the packets, if it is not properly ordered, if it is not properly orderly received, it should be reordered at the destination with the help of a sequence number. So once the errors are detected, the destination will be requesting for a retransmission. Okay. So on other hand,
है ना 30% चार्जिंग फिर अगर पूजा डॉट स्ट्रिंग 7 मेरी मेल आईडी है टाइम लगता है तो कोई याद है
so please, if you disturb me, I'll just remove you from the meeting and lock the meeting. Okay, I'll not repeat it again. I'll just remove you and immediately I'll lock it. Dinesh, Dinesh, can you please unmute? Should I want to remove you once again? Dinesh, so if you're not answering, I'll just remove you from the meeting, Kana. Are you there in the meeting? Simply
हेलो
connected and you'll be.
Ma'am, you're calling a wrong name. My name is Aryan, not Dinesh. So that's why I get confused.
You were the one not sure about it. I have to remember the name. I didn't remember. Okay, fine. So you can mute your audio bar. See, Kana, listen. If anybody disturbs, I'll not repeat it again and again. I'll just remove and unlock the meeting. It is a recorded meeting. Please don't make me to do all those what to say, teacher's responsibility or some other thing. I want to give a lecture. Please don't make me to see the recordings. No, take a note of the ones that keep on disturbing me, sending emails to the coordinators. Don't make me to do all those things. Okay. So on the other hand, what we were discussing, real time voice or video together with the video conferencing. All those applications, they need voice over IP calls, okay, or video streaming. So they can tolerate certain loss, right? So if even some data is lost, there is no any issue. So missing a few seconds, nanoseconds audio or the video frames doesn't break the conversation. Okay, so even it can introduce delays or lags. That that will not be a problem. So in that case, we'll be going for UDP protocol. Okay, so which will be sending faster data by skipping some of the error checking and retransmissions. Okay, likewise video conferencing. Video conferencing, they are delay sensitive, right? So timing is everything. So even a small delay can interrupt the flow of conversation. So in that sort of things, we'll be going for UDP. So UDP will be helps to minimizing the delay. TCP introduces the delay, but how come TCP introduces delay? With the help of acknowledgements and also with the help of retransmissions. Okay, but UDP will skip or it will reduce the delay by skipping, by ignoring the acknowledgements and retransmissions. Right? So the major cause of the delay variation is for the reliable delivery. So TCP is reliable delivery mechanism. So it will wait for the acknowledgement. If there is a packet with the error, it will ignore the packet, it will discard the packet and it will request the sender to retransfer the lost packet. Flow control is required. Okay, it can cause delay variation. Okay, so if I use in real-time applications, it will be very harmful. That's the reason we'll be going for UDP. So UDP avoids this by sending packets without waiting, and also it will be ensuring a smoother experience. So TCP is best for reliable, error-free communication, and UDP is best for fast and real-time communication. Right? So reliability in TCP. So what are how the TCP is giving the reliable delivery? So TCP, it is a reliable transport layer protocol. Okay, so the reliability can be achieved with all these things. The first one with the help of a sequence number. So every byte that is being sent, okay, it will be provided with a sequence number. Okay, so all the bytes will be assigned a sequence number. So this will help the receiver to reassemble the data at the destination. So it is a packet switch network. Okay, this is the sender and I take this as the receiver. Okay, so edge router, with the help of an edge router, these are network code. Okay, it will be connected as a mesh-like structure, isn't it? So it will send the packets This is how the connections will be there. So if the sender wants to send 3 packets, it is not necessary that all the packets will take the same path. Okay, so the first packet can take this path to reach the destination. The second packet can take this path to reach the destination. And the third packet can take this path to reach the destination. Okay, so that's the reason there will not be an order delivery. Okay, so the packet 1 is taking this path, packet 2 is taking this path, the packet 3 is taking this path. So the packets can received in this order, may receive in this order 3, 1, and 2. So with the help of a sequence number, it is the responsibility of the receiver to reassemble the packets. Okay, to reassemble in the correct order if the packets are received out of order. Okay, so the next one with the help of acknowledgements. So after receiving the data, what is the responsibility of the receiver? The receiver has to send the acknowledgements ACK. Fine. So if the sender is not sending, if the sender immediately after sending the packet, it will start the timer. Okay. So within the timer expires, if it gets the acknowledgement, then that's okay. So it will retransfer the second packet. Okay. The next packet, which are there in the buffer, that will be transmitted. Right. So if within the timer, if the acknowledgement is not received, in that case, the expiration of timer, it will trigger the retransmission. Okay. So acknowledgement numbers, it tells the sender. So what is the acknowledgement number? Acknowledgement number always, it tells the sender which byte expected next. Okay, that is very important. So if the sender is sent a packet with a sequence number 1000 to 1500, what will be the acknowledgement number? ACK will be 1501. So it informs the sender from 1000 to 1500, all the bytes I've received. So I'm expecting the next number, that is 1501. Again, the sender is sending, the receiver is sending 1051 to 1672. What will be the acknowledgement number? The next packet is with the sequence number 1501 to 1672. What is the next acknowledgement number, ma?
1673.
Yes. So 1673. Very good. So why it is 1673? It always informs the sender that I'm expecting this particular number. Whatever the packet that is being received, uh, till this, before this number, I've received all the packets and I'm expecting 1673. Okay, so this ensures the sender knows which data has been successfully received. The next one with the help of a timer. So TCP always uses timer to detect the packet loss. Okay, so always it will start the timer before sending the packet. It will start the timer. So it will send the packets. Within the timer expired, if it gets the acknowledgement, it will be sending other packets which are buffered. Okay, if not, this expiration of the timer definitely will trigger the retransmission. Okay, so the retransmission occurs due to two things. So acknowledgement due to network issues, acknowledgement would have been lost, or even the actual packet would have been lost. Okay, both the things will trigger the retransmission. So if the packet is lost, sending the retransmission is not a problem, right? But what about the acknowledgement? If the acknowledgement is lost, if I'm sending the same packet, how the duplicate can be identified? How to identify the duplicate, ma?
With the help of sequence number.
the receiver could able to identify with the help of a sequence number. And also the sender could able to identify with the help of a acknowledgement number. Okay, we'll see those things in detail. So same sequence number would have been received. So it will be expecting some other number, but the packet will be with the older sequence number. So it will discard it will consider that as a duplicate packet and it will discard the packet. So retransmissions, if the timer expires or if the duplicate acknowledgements are detected, TCP will be retransmitting the missing packet. Even the three uh, acknowledgements with the same number, it also triggers the retransmission. So in all these things will ensure the guaranteed delivery of the packet and duplicate acknowledgements. So duplicate acknowledgement when a receiver detects a missing packet, but continuously it is getting later packets. In that case, it will be sending duplicate acknowledgements. So say for example, so 1,000 bytes are sent in a one packet. Okay, so when the timer it is starting the timer, it is selective repeat, or else I'll take it as okay, selective repeat ARQ. Okay, so we have the congestion sliding window technique so that 5 packets can be transmitted at the same time. The receiver could able to receive multiple number of packets at the same time. So each packet are 1,000 bytes of length. Okay, so the receiver after receiving the first packet, it will start to buffer the packet. Okay, 1,000 to 1,001. Okay, fine. It will be buffering. So the next packet, it will check the order. So it is expecting 2001. So the received is also 2001. So soon it will be placed inside the buffer. So after receiving, due to some network issues, the packet 3 is lost. Okay. So after receiving the third packet, so what it is expecting? It is expecting, now it is expecting 3001. But what it is received at the receiving end 4001. Okay, so it will not discard the packet, rather it will be placing those packet in the order and it will send the duplicate acknowledgement, or it will send the acknowledgement like for this packet it would have been sent an acknowledgement 2001. For this it will be sending an acknowledgement 3001. For again it will be sending an acknowledgement 3001. So after receiving this packet also, what it will do, instead of saying, it will be storing in the proper order. Okay, it will not discard the packet. It will store it in that order, but it will be sending an ACK 3001. So all these, so these two things are duplicate acknowledgements, right? So already 3001 is received at the sender side. So these three acknowledgements, sorry, these two acknowledgements are duplicate acknowledgements. Once sender sees the duplicate acknowledgement, immediately it will send the corresponding packet, which are numbered 3001. So after getting this packet, it will place that packet in the order. Now it will be sending an cumulative acknowledgement. So ACK 6001. So this 6001 informs From 3001 to 6000, all the bytes are received, and I'm expecting 6001. Any doubts? Any doubts, ma?
No, ma'am.
Okay. So we have seen duplicate acknowledgements, and the next one is buffering. So buffering, TCP uses buffers on both the sides, sender side as well as destination side. So this buffers will be acting as a storage, that too as temporary storage for storing the data. So before sending the packets, everything will be buffered. The packets will be buffered. Okay. And then it will be sent. So in order to ensure the smooth data flow and smooth recovery, the buffers will be used. And we'll be using sliding window mechanism. TCP will be using sliding window mechanism. So sliding window controls how much the data can be sent before getting an acknowledgement. Okay. So in order to handle the flow control, sliding window mechanism is handled by TCP. Okay. So the TCP, in order to ensure the flow control, it will be adjusting how much data can be transmitted based upon the receiver capacity. Okay. So sliding window mechanisms, there are two sliding window ARQs. One is go back in. Go back in. If one packet is lost, the TCP goes back and it will transmit all the packets. So in this scenario, if the third packet is lost, it will discard fourth and fifth, and it will be requesting for all the three packets. Okay. So even if they were received correctly, everything will be ignored, and the receiver will be requesting all the packets from the order delivery in an order. Okay. That is the go back in. The next one is selective repeat. Selective repeat, this is an example of selective repeat ARQ. So the TCP use the selective repeat. So if one packet is missing, so it will be sending a duplicate acknowledgements. With the help of a duplicate acknowledgement, it can receive the one which is missed. Okay, so instead of retransmitting all the packets, whichever is missed, that will be retransmitted. So it will be ensuring the efficiency. To improve the efficiency only will be when compared to go back in selective repeat, it will improve the efficiency. So all these mechanisms together make a TCP a reliable protocol. So in order to ensure the data reached at the destination without any error, accurately, completely, and also in the order. So all these mechanisms are used by TCP. Fine. So the next one is flow control. So flow control, how the flow control is working in TCP. So flow control, what is flow control? In order to ensure the sender does not overwhelm the receiver. So the sender is a fast sender and the receiver is slow receiver. So if the sender could able to transmit 1000 bytes, okay, I have two bottles, one with 1 liter capacity, another with half a liter capacity. So if I'm pouring all the waters inside the half a liter bottle, rest of the half a liter will be wasted. The same way. So the sender is a fast sender and the receiver is a slow receiver. So if I'm sending 1000 bytes, but the receiver could able to receive only 500 bytes, next 500 bytes will be wasted. So I should not overwhelm the receiver, okay, with the too much of data. So that's the reason we'll be using the buffers. Fine. So this one shows the TCP receive buffer. Okay. So it is a TCP receive buffer. So receive, which will be working in the receiver side. So this buffer will be holding the incoming data. So until the application process the data, everything will be placed inside the receive buffer. Okay. So this is actually the available area to store the available bytes, available memory to store the receive data. Okay, so the data which are from the IP can be placed inside the spare room. This is the available portion. So this shows the data already there in the buffer. Okay, so it has to be taken by the application process. Okay, so waiting for the application to process the data. Okay, so this is a receiver window. So the receiver window represents the available buffer space. So how much more data the sender can able to transfer. So the receiver window tells about the free space. Okay, so here three equations are given. The last byte received minus last byte read less than or equal to receiver buffer. So this ensures the data will be received but not at read does not exceed the buffer size. Okay, so this is the last byte received. Okay, this is the last byte received and this is the last byte read. So this should be less than or equal to the receive buffer. Okay, so the receiver window should be equal to receiver buffer minus last byte received, last byte read. Okay, so this will be your receiver window. Okay, so that's what we have represented. Okay, so the receiver window, it tells the sender how much free space is available in the buffer. So you can transfer the data which is less than or equal to the receiver window. Okay, so this will be continuously updated and it will be communicated with the sender with the help of a TCP header, right? And also there is one more condition, last byte send minus last byte acknowledge should also be less than or equal to receiver window. So the sender must ensure that the number of unacknowledged bytes does not exceed the receiver window. So the last byte send and also the last byte acknowledge should be less than or equal to receiver window. Okay. So if the receiver window becomes 0, the sender passes the transmission until the receiver advertises the large window size. Okay, so this is how the TCP flow control uses the receive window, and also it will be adjusting the receiver window, preventing overflow at the receiving end. Okay, so in order to ensure a reliable communication, the receiver window is used here. Okay, any doubts now? Any doubts?
No, ma'am.
So the next one, we'll see congestion. So what is congestion? So congestion, so see here, this is sender 1, I'll take sender 2, this is router, this is receiver 1. Okay, from sender 1 to router, the link capacity is 10 Mbps and sender 2 to router, the link capacity is 100 Mbps. So multiple sources are sending the data in the network. Okay, so this source is capable of sending 10 Mbps. The link capacity is 10 Mbps. Here the link capacity is 100 Mbps. Okay, but both is merged at the router and it is converted into 1.5 Mbps. So this creates a bottleneck link. Okay, so the combined data rate, it exceeds what the shared link can handle, right? Imagine 100 Mbps and 1.5 Mbps. If this is sent one packet with a capacity 100 Mbps, it has to broken down into at least 75 number of packets. Imagine. So all those things has to be stored inside this router. So the router could able to have the rest of the packets buffered inside the memory. Okay. So this will definitely lead to congestion. The buffer space running out, the buffer will be running out of the space if both the senders are sending the data at the same time. Okay. So it can have only 100 Mbps of data, the buffer size. So since this link capacity is 100 Mbps, it can hold 100 MB of data, right? So 1.5 Mbps will be sent and the rest of the things will be there inside the buffer. Again, the sender is sending, sender 1 is also sending 10 more MB of data. What will happen? There will not be available buffer, right? So some packets would have been dropped. So if packet is discarded, definitely it leads to congestion. So what will happen? So the sender will try to, it will start the timer and it will send the packet. So it waits until the timer expires. Soon the timer expires, it will retransfer the packet. So it will not know whether the router is going out of the buffer space. Immediately it will be sending the packet. Soon S2 is also sending the packet. Okay, what will happen? The, here the buffer space will be overflowing and all the packets which are being sent by both the senders will be discarded. So multiple number of dropping the packets. So timer will be expiring. Multiple times retransmissions will be triggered. So at one stage, it will lead to congestion. Okay. So different sources will be competing for the resources. So each sender wants to transfer the data, but it is a shared common network, right? So competition will happen. So will be buffer will be out of it will be running out of the space. Bandwidth will be wasted. So the routers and the links here they have a limited capacity, right? So 1.5 Mbps link is very much smaller when it is compared with both the links 10 Mbps and 100 Mbps. So arrival of packets will be stored inside the buffer. Everything will be queued. So sometimes it will be dropped. So dropping of the packets will trigger the retransmission. Timer expires, trigger the lead transmission. At one stage, it leads to congestion. So no coordination will be existing among the sources. So each sender assumes it has a full link capacity. It causes the overloading, right? So performance will be degraded, the packets will be delayed, dropped, throughput will drop, latency increases. So overall network performance will suffer, right? So the congestion, when the congestion is happened, so the congestion always happen when there is a demand exceeding the capacity, right? So this is the bottleneck link which will be handling the congestion, which definitely it will trigger the congestion. Okay. So this is one of the major issue in the network. It requires certain flow control, congestion control, traffic management. Everything should be there. So performance degradation will happen. Fine. So congestion collapse and causes. So congestion, one of the most severe network problem is the congestion collapse. Right? So what is congestion collapse? So congestion collapse is nothing but it will occur when the network is heavily loaded. Okay. So more number of packets are transmitted. All the sources are sending the packets, but the routers, intermediate routers, they are running out of the buffer space. It will drop the packets. Dropping the packets will trigger the timer will expire. The timer expire will trigger the retransmission. Okay, so if it is happening again and again, definitely it leads to congestion, right? So more data is being injected into the network, nothing will be useful. Okay, only less packets will be transmitted and the others will be dropped. So it increases in RTT, it will trigger the packet drops, the buffer becomes full. So packet drop will happen. Packet drop, once the packet is dropped, uh, the timer will expire. If timer expires, it will trigger the retransmissions. There will be more number of packets in the network. So it definitely it will cause the congestion. So what are the possible causes for the congestion? So if a new transfer begins and it sends a large amount of data, okay, it will trigger the congestion. Okay, undelivered packets that to a large amount of packet trigger the congestion. Fine. And increases RTT. If RTT increases, it will trigger the congestion. Packet losses, retransmissions, everything. Okay. So first one is undelivered packets. So the packet which are consuming a bandwidth, a larger number of bandwidth, but it is not reached at the destination. Okay, it will trigger the congestion. And also retransmissions. So unnecessary retransmissions will increase the load. Again, it will degrade the network. Retransmissions in flight packets, definitely it will next stage is taking to the condition, fragmentation. So the large packet, if it is getting fragmented, the rest of the parts has to be placed inside the buffer. That's what I have explained in the previous slide. So 100 MB of BS of data has been sent. So the router could able to store 100 MB of data, right? So it will be fragmenting multiple number of packets. How much number of packets it has to be fragmented? 100 divided by 1.5. So 67 packets are required, right? So it will fragment this one packet into 67 packets. Why? So this link is capable of sending only 1.5 Mbps of data, right? So it will convert this one packet into 67 packets. Only one packet would have been sent and rest of the 66 packets will be there in the buffer. Okay, so if the large packet is being sent, it requires fragmentation. So one will be sent and rest of the things has to be stored inside the buffer. So if some other source is sending the packet, some of the portions will be uh, due to buffer capacity. Rest of the available, there will not be any available buffer space inside the router's buffer. So some packets would have been dropped. So it will trigger the timer. A timer expires, it will trigger the retransmission. And also the control traffic. So the routing updates like DNS, ERP, all these things will add the traffic. Okay, that too in network instability. Definitely it causes the congestion. And due to limited resources. Limited resources in the sense, the routers are, of course, they are networking devices, but they are not servers which will hold sufficient buffer space. They have a limited memory capacity. Routers, they have insufficient memory, and also they have slow processor, okay, and also lower bandwidth lines, right? So all these things definitely leads to congestion, and also due to bursty traffic. Bursty traffic, internet always it is bursty, right? Suddenly spikes in traffic will occur, okay, so overwhelm the network quickly. That all of a sudden it will be dropped. So congestion collapse, it will not uh, only it focuses on too much traffic, but it also focuses on inefficient usage of resources. So definitely all these things will reduce the performance. So if the proper congestion control is not being given in the network, if the window size is not extended and exponential back off is not uh, set by the sender, all these things will lead the condition. So the TCP should adjust the window and also it should go to the exponential backoff, okay, in order to prevent the congestion. So this is the congestion control. Congestion control, how to increase the network performance. Okay, so the goal is to maintain the number of packets in the network in a reasonable level. Okay, so that the throughput remains high and the delay becomes very low. That is our ultimate goal. So the throughput should be controlled and also the delay should be minimized. Okay, so too many packets, if it is there in the network, the buffer overflow will happen, the packets will be dropped, the retransmissions will happen. So it will take to the congestion, right? So first we'll see the throughput. So it shows how the throughput behaves in an appropriate load. So the first we'll take the ideal case. So ideal case, the throughput increases, right? So the throughput increases linearly. So this is actually the linear load, okay? And the network, it is never getting collapsed, okay? And the next one, it is a controlled throughput. So control, proper congestion control mechanism is there. So throughput grows steadily and it is becoming stable at one point. Okay, so if it is nearing the maximum capacity, the threshold value is set. So 75 percentage, if I'm taking 75 percentage is a threshold value, it stabilizes the control. Okay, stabilizes the throughput. And the next one is uncontrolled behavior. Uncontrolled, the throughput rises linearly. Okay, so after a certain time, it drops drastically. So see here, it is getting dropped due to congestion collapse. So this, if the congestion control is not properly taken place, definitely the throughput will be dropping. So it reduces the performance, right? So if we take the delay, average packet delay. So for the ideal state, so delay, it is gradually, it is growing, okay, and it is we can easily predict it, okay. The next one, the controlled delay, which is represented in a green line. So it is reasonable, and when it reaches the threshold value, it is being limited, okay. So increases, if it nears to the congestion, with the help of congestion avoidance mechanism, it is stabilized, okay. So once it reaches the threshold, that has been stabilized. What about uncontrolled the delay? Yes, after reaching a certain point, the moderate delay becomes it is increased. So the queues are filled up, retransmissions, network instability is happening. So the delay is getting increased. Okay. So the congestion control, it helps to avoid overload, and also it helps to uh, give the better performance. So it keeps the network in a stable state and also in a fast responsive when demand is getting high. So with the help of protocols like TCP, if it is getting implementing congestion control mechanism. So the control mechanism will start with a slow start, and it goes to the congestion avoidance state so that the window size can be adjusted. So all these things will prevent the congestion. Okay, it will avoid the congestion. Okay, any doubts, ma? No, Vikash. What about others?
Ma'am, can you please explain it once more, little briefly?
Which one, Gana?
This congestion control.
These two graphs.
Yeah.
Okay. So throughput, what is throughput? You know what is throughput and what is delay, right? What is throughput, ma?
Um, Throughput is usually the amount of data output.
A delay?
Delay, time delay, I guess.
The throughput is nothing but the data that is being sent successfully. That is your throughput. Delay, the time it takes the packet to travel from source to destination. That is the delay. Okay. So
Okay.
the ideal state where the congestion is not happened. Okay. It is very ideal. There is no congestion at all. Okay. So the throughput is getting linearly increased. Okay. So at one point of time, the network never collapses and it is steady. Okay. It is retaining one. So the network is not having heavily loaded packets. It is a reasonable packets. So throughput increases starting from 0 to 100 percentage, and steadily it is being maintained 100 percentage. Okay. So I'm not putting large amount. If the link capacity is 50 Mbps, and all the time I'm sending the packets which are less than 50 Mbps, so it goes to the idle state. So the required capacity is greater than the whatever that is required. So my actual capacity is greater than whatever that is expected. So that is the ideal state. The next one is control state. Control state in the sense there is a congestion avoidance technique that is being implemented. So I'm not the congestion avoidance. It will go to the prevention state. So once it reaches the threshold, 75% is the threshold value. So once it reaches the threshold value, it will control the network throughput. Okay, it will not increase the throughput once it reaches the 75% of the throughput. Okay, in the network, entire network. So if 50%, what will be the 100 Mbps? What will be the uh, throughput? 75 Mbps. So it will not take much more than 75 Mbps. So we can give a controlled data flow. Okay, rest of the things, it will inform, the center will be informed with a bit. Okay, so much more mechanisms are there in order to inform the sender to slow down the transmission. So if it reaches the threshold, if my buffer size becomes large, 75% of my buffer is being filled, the router buffer is full, immediately it will be informed to the sender. So with the help of an acknowledgement packet that is being transmitted from the receiver to sender, that packet will be enabled with 1 bit indicating that you have to slow down the transmission. So the sender can able to slow down the transmission. So this transmission, the throughput will never gets increased. But if it is not controlled, what will happen? Suddenly, all of a sudden, uh, everything will be collapsed. Retransmissions will be triggered. Buffer size will be exceeded. Soon, the throughput decreases. So all the packets that have been transmitted, everything is dropped by the discarded by the router. What will happen? The throughput becomes zero. Fine. Any doubts?
No, ma'am, not really.
The same happens for the delay now. So if it is idle, my required capacity, actual capacity is greater than the expected one. Okay, I need 100 Mbps of data, but I have 200 Mbps of link capacity. Definitely it will take to the ideal state. And the control state, I'll have an congestion avoidance mechanism. So I'll have a threshold value. So once it reaches the threshold, I'll inform the sender to slow down the transmission. So the delay will be maintained as such. So if it is not controlled, definitely the delay gets increased. The gap between the sender and the receiver, the packet, uh, will be there, always there in the router. Sometimes it will be discarded. Sometimes it will trigger the retransmission. So the delay becomes very large. Right? Any doubts? Shall I continue?
No, ma'am, now I got it.
So what are the solutions for congestion control? So solutions like, so when dealing with congestion in network, we have to follow two major approaches. One is open loop control, and the next one is closed loop control. So open loop control to prevent the congestion. Okay, so preventing the congestion before it is happening. That is the open loop control. And the closed loop control, once it is congestion is happened, we have to react, and we have to take the network recovered after the congestion has been occurred. Okay, that is the difference between open loop control mechanism and closed loop control. So open loop control, it focuses on uh, the design time decisions, likewise traffic management policies. So the system will be configured to never the network enters into a congestion state. So traffic shaping, admission control, resource allocation, all these things happen to prevent the congestion. The next one is closed loop control. It uses a feedback mechanism. So in order to recover once the congestion has happened. So we have to detect the congestion in the network, and we have to send the feedback to the sender, and we have to take the corrective action. Okay, to reduce the transmission rate. So congestion control mechanisms, TCP will have three states: slow start, and the next state will be two phases will be there: slow start phase and congestion avoidance phase. Okay, so we'll see in detail. Before that, we'll see open loop solutions. First one is the leaky bucket. Okay, leaky bucket algorithm, it is an open loop method which is used to regulate the traffic flow and to prevent the congestion. Okay, so this is an example link of the network interface. So if I'm taking that as a bucket with a small hole at the bottom, water here it represents the packets. Okay, so packet is dropped into the bucket. Okay, all the time it is being leaked. Okay, at a constant rate. The water is leaking at a constant rate. Okay, so all the time here, this rate is not a particular rate of transmission. It is not restricted to particular limit, but inward flow is not restricted, but the outward flow is restricted. So if the bucket fills up in a faster way, it will be leaking at a constant rate. Some of the back packets will be discarded. Why? Because some water it overflows, right? So this is the leaky bucket technique. Okay. So here I'm taking the host a computer which is sending the packets. Okay. All the packets are sent to the system, and it is it is an unregulated flow. It is not restricted. So these buckets will be placed inside the buffer. Okay, that is a leaky bucket at the network interface. So at every clock time, only one packet will be transmitted. Okay, so if the bucket is full, what will happen? When a new packet arrives, it will be discarded, right? So my bucket can hold up to 5 packets. Already 3 packets are there in the queue. So even if I'm adding 3 more packets, 2 packets would have been added, and the sixth packet will be discarded. Okay, so the inward flow is not restricted, but the outward flow is restricted. So if the buffer becomes full, if a new packet arrives, definitely it will be discarded. Okay, the outward flow will be output rate is steady, even if the input rate is bursty. So this will guarantee the network will be going in a fixed, predictable stream of packets. Okay, so of course, making congestions uh, much when compared to the previous one, it will be reducing the congestion. Okay, so incoming busty traffic is smooth here. Why? Because we are restricting the outward flow. Okay, so the consistent traffic will be there. So one packet per clock tick will be sent out of the buffer. So of course, overflow will happen. This will trigger the transmission, retransmission. Sometimes again, the network congestion will leak, but not in that exponentially. The congestion will be reduced here. Okay. So this is another algorithm, that is token bucket algorithm. So that is leaky bucket algorithm. The next one is token bucket algorithm. This also comes under open loop congestion control mechanism to prevent the congestion, to allow the control busty traffic. Okay. So there is a bucket will be holding the tokens. So these are the tokens. Okay, these are the tokens. Okay, so one token will be added at a regular interval. So if I'm taking del t as a regular interval, so at that time period, so every 30 seconds or every 1 minute, okay, a token will be added into a bucket. So in order to send a packet, if I want to send one packet, a token will be captured and the packet will be sent. Okay, so the token will be regenerated after 1 minute or after 30 seconds. That is after del t time. Okay, so if no tokens are available in the bucket, so the packet must wait. Okay, so this way the packets can uh, send only when the token is available. Okay, so this is the if the host wants to send data and there is no bucket, sorry, no token in the bucket, it has to wait. Okay, so whenever the token is there, it can able to send the packet. So when needed, the host can use all the saved tokens to send the burst of packets. Okay, so flexibility will be increased when compared to the leaky bucket. Okay, so it will be sending a fixed rate of data flow. Okay, so here the host is transferring the packets. Okay, so if the tokens, so in this example, 5 packets are coming in. Okay, so the host wants to send 5 packets, but in the bucket, only 3 packets are available. So these packets will be acquiring it takes the token and the packets are transmitted. So rest of the 2 packets, they are waiting. Okay, the host cannot send the packet, it is waiting. So once the token is regenerated after del t time, the packets can be transmitted. So it will ensure the average rate is controlled. Okay, and the short burst always it is permitted. Any doubts, ma?
No, ma'am.
Now we'll see closed loop congestion control mechanisms. Closed loop congestion control mechanisms. The first one is a warning bit. Already I've told you. Already I've discussed the warning bit. Okay. It is a feedback based method which is initiated by the routers. Okay. So I have a sender one. This is router one, router two, router three. Much more. This is receiver. Okay, sender and receiver are connected by 3 routers. So it is a feedback-based mechanism initiated by the routers in the network. So whenever whenever a router is detecting the congestion, for example, the high queue length or the buffer is flowing out of the it is running out. In that case, it will be setting a special bit in the packet header. So that bit is called as a warning bit. Okay, so the packet is being transmitted, and the packet one is transmitted by sender. Okay, so R1, R2, and R3 is there. So R2 here, it is having a buffer size. So already 50% of the buffer size is full. Okay, so after receiving this packet P1, so the fragmentation is required and one portion of P1 is transmitted and rest of the portions are saved inside the buffer. So again, it takes another 25 more percentage of the buffer space. Okay, so what is the available space? 25 percentage. If I'm setting the threshold value to be 75, so what it will do is in the packet header, it will be setting the warning bit to 1. Okay, so the congested router, here it is the congested router, right? It will be setting the warning bit to 1. Okay, so this will be reaching the receiver. The receiver will be copying this warning bit in the acknowledgement, and the acknowledgement will be reached to the sender. So in the acknowledgement, the warning bit will be set to 1, right? By seeing this, the sender will be reducing the transmission. So once receiving the acknowledgements with warning bits, the sender will become aware of congestion. Immediately, the sender will gradually it will reduce the transmission rate. Okay. So before the packets are being dropped, this will happen. Any doubts? So it is a reactive mechanism. Sometimes congestion is detected and it will be reported and corrected. Or else, if I'm having a threshold value before that itself, we can stop the congestion. Any doubts, ma?
No, ma'am.
So the next one is choke packet. Choke packet. Choke packet is nothing but a control message. Again, this will be generated by the router. Okay. So choke packet will be generated by the router in order to warn the source to slow down the congestion. Okay. Sorry, to slow down the transmission. So the router will be continuously, it will monitor the utilization. Okay, so if the utilization exceeds, so it will have a threshold value. So once the threshold value is reached, if it exceeds the threshold value, so the router will be identifying that as a congested state, and the router will be sending a choke packet. So choke packet, it is this packet will be sent back to the source. Okay, so this packet will be in the best example is the source quench packet. Okay, I see MP source quench packet is an example of a choke packet. Okay, So in order to, the choke packet will contain which is the destination, okay, which is the source, what is the flow, so which flow is causing the congestion. All the details will be there in the uh, choke packet. So once the source receives this choke packet, it will reduce the transmission. Okay, so instead of sending much more packets to the corresponding destination, it will slow down the transmission. So it will minimize the congested router uh, uh, by putting much number of packets to it. Okay, but there is issues in choke packet as well. So if the choke packet is a delayed packet, so if choke packet becomes a delayed choke packet, itself it is delayed. In that case, the source will continue to send high volume of traffic. So again, it leads to congestion. So hop by hop and end to end, some designs requires hop by hop show packet. Intermediate routers should be react in a faster way so that it can be communicated to the end of the communication. So non-cooperative sources, if a source if it just ignores the source packet or fails to respond appropriately, of course, there will be a congestion. Right? So where to prevent the congestion? Congestion can be controlled in both the way, proactively as well as reactively. So it is the responsibility, it relies on both the ends, at the sender end, by end host, and also by the router. So end host are nothing but the client servers, everything. So they have to adjust the amount of data that is being shared, or else they have to take the feedback from the network. Okay, with the help of an acknowledgement, with the help of a warning bits, dropping the packets, congestion notifications, everything they have to react. So protocol like TCP, uh, TCP, it has built-in mechanism. So it starts from slow start, congestion avoidance. With that, it will be adjusting the window size to adapt the sending rate dynamically. But what in case if it is not happening? So if it is ignoring those informations, definitely the congestion cannot be prevented. So this approach is an end-to-end so that it will regulate the traffic before the congestion happens. The next one at the router end, router are the core of the network. It is at the center of the network. Okay. So this is the responsibility, the higher responsibility is there for the router to detect the congestion early. So they can send explicit indications like warning birds, choke packets. Okay. So packet drops. So all these things can notify the sender about the congestion. So the routers can implement the fairness mechanism to prevent who are the well-behaved sources, which are greedy, which are misbehaving. So which packets has to be dropped, early detection. All those things must be promptly done by the routers. Okay. So congestion control and avoidance. What is congestion control? What is congestion avoidance? So congestion control and avoidance is nothing but it is a mechanism to ensure the resources are used effectively. We are allocating the resources, allocating the bandwidth fairly among all the routers, all the users, preventing the congestion collapse, everything. Okay. So efficient, the first one, efficient use of the resources. So congestion control, it ensures the bandwidth, buffers, processing capacity, everything are effectively used. They are fully used. They are not reused. They are effectively used. So to get the maximum throughput, okay, without flooding the net. The next one, preventing the fairness in the allocation. So fair resource allocation. The goal is to allow all the users are given a fair share of the available networks resource so that the congestion is not happening. Okay. So monotonically, I'm not allocating, I'm not, uh, you would have studied in operating system. So when deadlock will happen? In the starvation. So if Always, if I'm giving priority for only one particular user and I'm not, the network is not considering rest of the routers, definitely it leads to congestion. I'm not fairly allocating the resources, right? And also we have to prevent the congestion collapse. So when the network becomes overloaded, the packets are getting dropped or delayed, the performance will drop drastically. So in that case, there should be implementation of the congestion mechanism to both prevent and to avoid. So if the sign of congestion is detected, we have to prevent the collapse before it is happening. So congestion control and avoidance, we have to balance efficiency of the resources to be used properly in order to give throughput, maximum throughput. Fairly, the resources should be allocated to prevent the starvation, and stability must be there for uh, avoiding the congestion collapse. Okay. Any doubts?
No, ma'am.
No, ma'am.
Now we'll see TCP congestion window. Okay, so it is a key mechanism in TCP congestion control strategy. Okay, with the help of congestion window. So every sender, TCP sender, will maintain a congestion window. Okay, so the maximum number of bytes that can be sent but not yet acknowledged. Okay, so the data that can be transmitted, that will be intimated with the help of congestion window. So it will be acting as a dynamic control on the sending rate to adapt to the current network conditions. Okay, so how it works? So the first one, what is the goal? The goal is to find the right sending rate. Okay, so if no packet loss is detected, the TCP will increase the congestion window size. Okay, if there is a packet loss, in that case, the TCP will reduce the congestion window size. So this increase and decrease strategy will help the TCP to regulate, to adjust the throughput so that the congestion is not being happened in the network. Okay, so this mechanism will work without needing any explicit network feedback. So from the routers or from any portion of the network. But there is a disadvantage. So it is a reactive TCP. Sometimes it misunderstands the sending rate. So this can lead to congestion or underutilization. Okay. So the window, with the help of congestion window, the TCP can regulate the behavior. Sometimes it will misunderstood and sometimes it goes wrong as well. Okay, now we'll see an example so that you can understand very well. So TCP congestion control, track and transit data. So TCP will monitor uh, the amount of data which are being transmitted. So the data that has been sent but not acknowledged, everything will be keep in track. So it will be using a dynamic parameter. That dynamic parameter is called as a congestion window. This will limit the amount of data that is being put it inside the network. Okay, so sending condition, we have to follow the sending condition. So sending condition is last byte sent. Last byte sent minus last byte acknowledged should be less than the congestion window. So this ensures the sender does not overwhelm the network by sending too much of data at once. Okay, so the effective window size, the sender's actual transmission window will be considered by two main factors with the help of a receiver's advertised window. That is, receiver's advertised window is RWND, right, based upon the receiver's buffer space. Okay, and also the congestion window, that is CWND. So whichever is maximum, that will be considered. Sorry, maximum size that will be considered. So sender's maximum window size. The sender's window size should be minimum of the advertised window. That is advertised window, nothing but the receiver's window size, comma the condition. Whichever is minimum, that will be taken as the window size. Okay. So the last byte sent minus last byte received should be less than or equal to this window size. That is minimum of the congestion window and the advertised window. Okay, so if the congestion window is small, the TCP will be sending less or preventing, it will prevent the congestion. But if the receiver window is small, in that case, it will prevent overrunning the receiver's buffer. So dynamically, the TCP will be adjusting the window size, either the congestion window size or the advertised window size based upon the network feedback, like acknowledgements, time modes, in order to balance the throughput. Fine. So now we'll see how the TCP regulates the data flow using the congestion window, that is CWNT. So this is the last byte acknowledged. This one represents the last byte acknowledged. So the data that is received by the receiver, this confirmation is sent. Okay. So this, it is already sent, but waiting for the acknowledgement. Okay. So this portion of data is sent to the receiver, but not yet acknowledged. Okay. It is in flight. And this, the last byte sent so far, which is sent already, that is mentioned here. The entire region in flight, the data is limited by the condition window. Okay. So which defines the maximum number of acknowledged packets that can be allowed. Okay. So the sender only sends if and only the last byte sent minus last byte received should be less than or equal to the congestion window. So what is the congestion window? This portion is called as the congestion window. Okay, the entire portion is called the congestion window. So the network does not get the overloaded number of packets. So if this is limited, if this limit gets exceeded, the sender has to wait for acknowledgements for pushing more number of data. So if it is not acknowledged, it has to wait for certain time so that once it gets the acknowledgement, it can send the data. Okay. So congestion window, it is not an fixed one. Here it is a dynamic one. It changes dynamically based upon the network conditions. So the TCP will increase the congestion window gradually if there is no loss, and it reduces the congestion window if it detects the congestion. Okay, so congestion rate of transmission will be congestion divided by RTT, number of bytes. What is RTT? What is RTT, ma? You know what is RTT? You know trace route command, right? So I'm tracing the route from my system to the nearby Google server. So how much intermediate routers are there? What are their IP address that are being traced here? So these are the IP address. Okay. So tracing route. So if there is long delay, that will be indicated with star. Always ping will send 4 number of packets, okay, 3 to 4 packets, and the same packet will be. So see here, there are 3 packets, 4 packets which are being sent. Okay, the packet number 1, packet number 2, packet number 3, packet. How many packets sent? 4 packets sent, 4 packets received. There is no loss. What is the RTT? RTT is nothing but round trip time. The time it takes for the packet to reach the destination, and also the time it takes for getting an acknowledgement. Together, what is the time? That is called as round trip time. The minimum time is 61, maximum is 681, and the average is 72. So what is RTT?
Round trip time, ma'am.
It is round trip time. Okay. So if my congestion window size is larger and the round trip time is smaller, I'll be getting a faster TCP. Fastly, the rate can be transmitted. The rate increases, the TCP can send the data in a faster way. So this should be balanced with network feedback to avoid the congestion. Okay, so congestion window, it defines how much data can be in flight. So it will be adjusted automatically to keep throughput higher, but the congestion in a lower state. Okay. So what is the basic principle? Packet conservation. So the foundation of TCP congestion control is packet conservation. So for every packet that leaves the network, the sender should inject exactly only one new packet. Okay, so if it leads to self-pacing. Okay, so where the sender naturally adjusting its rate to match the network capacity. So this can be ensured. We can ensure stability if the congestion in the congested network by avoiding a busty traffic or maintaining an equilibrium. Okay, so if one packet is being transmitted and if that is not acknowledged, okay, so only one more packet should be placed inside the network. Okay, for every packet that leaves the network, it gets acknowledged. Okay, the sender should inject only one exact packet. I'm sending the packet. Okay, so for this packet, I'm getting an acknowledgement. So for this packet already been sent, I can send only another more packet. So if I'm transferring 2 packets, for both the packets, I'm getting an acknowledgement. 2 more packets can be transmitted, which is called as self-pacing. Okay. And also at the beginning of the connection, after packet loss, the TCP does not know the network's capacity. So in order to ensure, it should start with slow start state. Okay, so where it doubles the congestion window every round trip time. Okay, the exponential growth can happen. So round trip timing, it stays at equilibrium. Once equilibrium is reached, threshold value is reached, the TCP uses RTT measurements for maintaining the packet conservation. So the data is sent only after acknowledgements. Right? And the next one is the congestion avoidance state. TCP will be shifting to the slow start state from the congestion avoidance state. So once it exceeds the limit threshold value, it moves to the congestion avoidance state. So it applies the additive increase, multiple decrease algorithm. So additive increase is gradually it will increase the congestion window. Multiple decrease is once the packet loss happens, half of the congestion window size it will be reduced. Okay, we'll see an example. This is the slow start state. So for one packet sent here, slow start, the congestion window size is 1. I'm sending one packet. For that packet, I'm getting an acknowledgement. So now I can double my congestion window size. So I'm doubling the size. So 2 packets are transmitted. For both the packets, I'm getting an acknowledgement. Again, I can double. Okay, so 4 packets can be transmitted. For all the 4 packets, I can get the acknowledgement. My threshold, say for example, my threshold value is 4. Okay, once it reaches the threshold value, what will happen? The slow start state will end and the TCP will enter into congestion avoidance state. So what is congestion avoidance state? Congestion avoidance state, linear growth will happen. So once it reaches the threshold, instead of doubling the congestion window size, it will increase the congestion window size only by 1. Okay, that is additive increase. That's why the name is given as additive increase. Okay, so we'll see an example. This is uh, how the TCP Tahoe works. Okay. So TCP Tahoe, it starts from the slow start state by setting the congestion window as 1. So getting an acknowledgement, now the congestion window becomes 2, 4, and 8. Okay, threshold is 8. So I cannot double the window size. Now this is the slow start state. From here to here, it is slow start. Now it is moving to congestion avoidance state. This is the congestion avoidance state. So it goes to additive increase from 8, 8 plus 1, 9. From 9, the congestion window size is increased to 10 and it is increased to 11 and it is increased to 12. Here the congestion has happened. Okay, I'm not getting an acknowledgement for 1 or 2 packets. So immediately what your TCP Tahoe will do is immediately it drops the congestion window will be dropped and again it will start reset the congestion window to 1 and it will start further and once it gets reduced the congestion window half of the window will be set to the threshold value. So my uh, congestion window size is 12. Window size divided by 2, that is 6. 6 will be your slow start threshold value. So it will be taken as a slow start threshold value. So see here 1, 2, 4, then it becomes 6. After that 7, 8, 9. Okay, so this is how the TCP Tahoe works. Okay, the next one is TCP Renault. TCP Renault works in a different way where the slow start state and congestion avoidance state is same, but once the congestion is detected or 2 or multiple number of packets are not being acknowledged, in that case, the half of the window size will be taken and that window size will be set to threshold and also to the congestion window size. Okay, so it will not drop the congestion window entirely to 1. Okay, it will not start from 1, but instead half of the value or the current window size will be considered. Half of the current window size will be considered for both the threshold value and also for the congestion window, and it goes to the additive increase. Okay, so this is additive increase. This one is multiplicative decrease. Okay, any doubts, Ma? Do you have any doubts? I want to repeat it once again. Any doubts?
No, ma'am.
Detecting and reacting to losses. So how the TCP detects the packet loss and how it responds to maintain the stability. So it can be detected with the help of timeout. So if the timeout happens, the sender can identify the receiver did not receive the packets. Either the packet would have been dropped, due to network congestion, the packet would have been discarded or acknowledgement would have been discarded for a packet within the expected time. So the TCP assumes this happens due to congestion. So if timeout happens, the TCP will understands this happened due to congestion. So the TCP, what it will do is it will reset the condition window size to 1 MMS. Okay, the condition window size starts from 1. Okay, it will restart again, start again, and it grows exponentially. So this is how the Tahoe works. But how TCP Reno works? Reno works in a different way. So three duplicate acknowledgements. If three duplicate acknowledgements are received, the TCP Reno will understand this is not happened due to congestion. So this acknowledgements it may happen due to one segment, one packet is actually one packet was lost, and it is not severe and this not happened due to congestion. So instead of reacting immediately, it will set the half of the congestion current window size will be taken, that will be set to the threshold, and also it will be considered for the current window size. So it will cut the cutting condition window in half, and that will be considered for the threshold as well. So, and also it enters to the congestion avoidance mode, additive increase mode. Fine. So this is how the Reno will do recover. It allows this allows Reno to recover faster without going back to the slow start state. That's the difference between Tahoe and Reno. That's what we have seen. So TCP fairness. So TCP fairness, added to two competing sessions are there. So connection 1 and connection 2. Okay, so both the connections, this diagram we have seen in the previous slides itself. Okay, so it goes to additive increase and gives, to see it, it goes to the linear exponential increase, and from here to here it is an exponential increase, but here it is a linear increase. So additive increase will give a slope of 1. Okay, so if throughput increases, it gives a slope, right? So this is slow start and this is additive increase. Immediately, if the packet is lost, it comes to the multiplicative decrease. So it decreases the throughput proportionally. Okay, again, it grows linearly. If there is any packet loss, multiplicative decrease happens. So this is how the bandwidth is being, it is getting increased and it is being dropped. Okay, so AIMD, it pulls the system closer to the equal bandwidth share point. Okay, so it prevents one connection from dominating the bottleneck link. So it will give fair and stable throughput allocation. Okay, so additive increase, it pushes the throughput higher for both flows. Multiplicative decrease, it responds to condition by reducing the sending rate. So the system will give you a fair, where all the connections will be getting a reasonable share of bandwidth. Fine. Any doubts, ma? Rest of the things we'll see in the next class. Few more slides are there. We can see in the next class. Do you have any doubts in today's class?
No, ma'am.
No, ma'am.
Thank you. Okay. If there is no doubts, you can leave the meeting now. Thank you.